on demand forecasting, inventory optimization, and distribution planning. I've been doing that around Barcelona first and then Boston. In Boston, I also did a master in supply chain management at MIT, where I've been working mainly on network design, data science for supply chain management, and of course, operations research, which is going to be one of the main content of the talk of today. As Marco said, right now I'm the co-founder and chief analytics officer at Cargoful, where again I'm working on machine learning operations research applied to the world of logistics. Just a very few notes on Cargoful. We are a seed stage tech startup based in Milan. We are building a very nice product. There is a transportation management system in order to help logistic companies optimizing their fleet operations. We are all engineers, so of course, if you want to reach us, we are very open to super technical discussion around what we're going to see today. Now, big question, why am I here apart from being invited by Marco? I'm here because supply chain management is a very complex discipline, and it's also a very data intensive discipline. So it's basically a very good field of application for advanced analytics techniques. And what I'm going to do today is really to go through some very interesting use cases in logistics and transportation. And I'm going to present how advanced analytics can really help companies solving very hard problems. There are many problems that are very hard and that logistics and transportation company face. I've presented here three main problems that we also solve at Cargoful, and during this meeting we're going to focus on the first one. So the first problem is the planning and dispatching problem. The idea is that a shipping companies which owns, for example, like 50 trucks, they have to deliver packages around a city, let's say Milan, to give an example that is close to us. And they have to do it, of course, in an efficient and optimal way. So the idea is that every day as a planning manager, you have the trucks, you know which packages you have to deliver, and you have to understand what's the optimal sequence in visiting the addresses. And also you have to know, for example, which trucks will do which delivery, and also how many vehicles are needed, of course, because we don't want to overinvest into assets which we don't really need. This is a very hard problem to solve, and this is one of the problems that we are gonna analyze in details today, and to see how advanced analytics, machine learning operations research can really help to solve this very complex problem. Another problem that we face is the driver scheduling, which is another very hard problem due to its complexity. The drivers shift, they are regulated quite intensively in Europe. So for example, a driver cannot exceed 9 hours of driving time, but there is an exception of twice a week. The total weekly driving cannot exceed 56 hours, and then there is another constraint on the maximum 90 hours over a certain horizon. And the idea here is that those constraints are very hard to be tackled by humans. They are very hard to be factored into a resource plan. So we need some advanced analytics techniques to make decision in a proper way. Another problem we face and we solve is the load finding problem, which is another very interesting problem that company faces when they ship to remote areas. So for example, let's say that my trucking company is based in Milan, but I ship to remote areas like Molise, which is where I come from. And it's very hard to get back to Milan with an empty truck. Why? Because there is usually no direct backhauls loads going from remote areas to logistics hubs like Milan. And the question here is really, how can I fill the truck with intermediate stops and try to overcome this problem? So again, those are very complex problems where we are going to see how to apply advanced analytics to make them, solve them. Those problems are hard for people because of many different reasons. Those problems are, first of all, computationally difficult to be solved. They are NP-hard problems. They are also dominated by uncertainty. So there are many variables that have to be taken into account at the same time, like, for example, customer demand that is changing every day, weather, traffic, and driver performance. And most important, regardless of the complexity, those problems have to be solved in a continuous way. So you don't do logistic planning one per year, once per month, or even not once per day, but those problems have to be solved on a continuous basis. Today, people really waste a lot of time doing solving these problems by hand or with inappropriate tools. And this really results in two big issues that we have in logistics right now, which is, on the one hand, the fact that fleet utilization is below 70% in Europe. So for 30% of the time, trucks are running empty. And of course, those activities are a waste of time because it takes a lot of time for people to solve these problems when technology is not supporting them appropriately. So at Cargoful, we are solving these problems with two different buckets of, let's say, models. And the idea is really to help people take a decision. Those two buckets are, on one side, operations research, and on the other side, machine learning. On the left here, in terms of operations research, what we do is that we spend time doing a lot of research in order to identify the best models and approaches. And the one that we have collected are mainly categorized here in three different categories, which are Metaheuristics, Constraint programming, and mixed integer linear programming. And we're going to see really how this mix is used in our software. On the other end, on the machine learning side, we mainly use supervised learning techniques and based on trees in order to really try to solve specific problems that we are gonna see in the remaining part of the session. A very important message that I would like to bring here is that in this case, our mission is really to cook the best possible meal out of those ingredients. So the idea is that we invest a lot of time in research, and we spend a lot of time in picking the best models, the best attribute approaches, the best methods which are available out there, and we cook them together so that our clients can really enjoy their meals in a very easy way into a product. So we do sometimes also one-off projects, but our main goal is really to bundle those technologies into products that people can use every day without being a computer scientist. So the idea is really to do a lot of work in research, in scouting of technology, and then bringing those ideas in a very concise and packaged way so that user can really use those difficult technology, even if they are not, they don't really have a deep technical background. So I presented before like three different problems, the planning and dispatching, driver scheduling, and the load finding. Right now in this talk, we're going to focus more on the first problem, which is the planning and dispatching. So again, here the idea is that we have to pretend to be like a logistic manager. So we own 50 trucks. There have been many orders that came to my company, which are basically orders to be delivered. So packages that have to go to certain addresses in Milan, which are most of the case home addresses. And the idea here is that I really need to have a way of doing this plan appropriately in an efficient way. Okay. And of course, I want to understand also how many vehicles are needed and what's of course the minimum number of vehicles that are needed to accomplish the job. What we do is that we have built like an integrated pipeline, which is based on machine learning and operations research approaches, which is made of 3 different steps. The first step is data collection. This is a very important step because we have to integrate different data sources in our system. In this case, there are 3 main data sources that we have to integrate into our data platform. First of all, we need to know who's going to do the delivery, so the trucks. And in doing that, we collect data mainly from the IoT devices, which are installed on the trucks, where basically we can read dynamic data such as latitude, longitude, fuel level, hours of driving, and so on. And alternatively, we can also read those data, of course, not the fuel consumption, but the geographical coordinates from the mobile app, which we can install on the phones of the drivers. So this is a first set of inputs that we use about who's going to do the delivery, so the trucks. On the other end, we have the deliveries. So we have to know what has to be delivered. And again, the idea as for the trucks is that data integration plays a key role in this case, because we have multiple sources. So data can come from company ERPs, they can come from manual creation of the user, which create data from scratch in our data platform, or they can also come from external load boards, which are providing open data to tracking company. Of course, an important component to consider is the regulation, because as I said, driver scheduling is a very hard problem to solve, and also driving time is very well regulated in Europe. So of course, this is something that has to be taken into account into the plan. A lot of effort in this case is really done by us in data engineering, and of course in building pipelines that make data flow from many different sources into a unique source of truth, which is our data platform. The second step of our pipeline is the geodata augmentation. What happens is that once I know which trucks are available, which deliveries I have to do, and how the regulation is gonna kick in the algorithm, I have to augment this data under a geographical point of view, which basically means to calculate duration and distance matrices, which is basically the key ingredient in any logistic planning task. So the first step in this case is, of course, to retrieve those distance matrices from a provider, but of course we have to enrich those matrices with some prediction based on historical performance, because of course not all the points on the map are going to behave in the same way, and we're going to see how machine learning can really help us in predicting duration and duration time in a better way rather than just reading a map. The third step in the end is the problem resolution, where basically we bring in all those inputs. So we have the data collection inputs on the one side, we have the matrices, the distance matrices on the other, and then we use our solver engine in order to create a delivery plan. Which is basically an idea of which truck is going to serve which point on our map. And also we can retrieve the order, the sequence of the orders that have to be done by each truck and each driver. In reality, the idea is really to give to each driver a to-do list of points to visit, which is of course done in an efficient way. So we have been able to minimize, for example, the total distance, the total duration, the number of vehicles, and we have a plan that is efficient and just have to be implemented. So let's deep dive right now on the prediction engine that we use to, let's say, augment the data with geographical considerations. The idea here is pretty simple. So basically, to make a delivery, there are two different things that we need. We have to travel to a certain destination. So we are going to spend a certain travel time going from A to B. But then once I get to B, I'm going to serve the client. So I'm going to spend some service time there. For the first component, which is the travel time, what we can do is that we can retrieve travel times from the usual map providers that we can use, like Google Maps here, OpenStreetMap, and so on. And those guys, they do a pretty good job at doing this. So they can give you a matrix, which is which includes all the distances between all the points that are included in our problem. What they cannot really do is to take into account what really happens when we get to a certain location. So they don't really know how much time is going to take, when I've arrived at point B to really deliver my package. A couple of examples here, staying in the last mile settings. Sometimes once I get to an address, it might be easier or harder to deliver a package depending on many different factors. For example, during a certain time of the day, it can be easier to deliver a package because it's easier to park around the destination. So the service time is going to be smaller. Sometimes it might be harder. So for example, when I'm going into an area which is very dense during a certain day in terms of traffic, then it's going to take a lot of time to deliver a certain package. So what we have to do is that we have to adjust the pure mapping data in order to take into account also the historical performance and what has happened to a certain location once I got there. In the long haul transportation, so basically for line hauls, which goes, for example, from Rome to Milan, then once I get to a certain warehouse, then the service time can still be different because different warehouses work in different ways, which basically means that it's going to take a different time to unload a certain truck depending on the efficiency that the warehouse of my clients currently have. So the idea in this case is really to collect historical service time using geocoding data, which can come again from the mobile app and from the IoT devices which are installed on the trucks, and try to predict on the basis of multiple predictors, like for example, the time of the day of the week, the month of the year, the density of the delivering area, trying to predict what the future service time can be. And as I said in the beginning, what we do here, it's we solve regression problems basically mainly using tree-based methods. Going back to the pipeline, the third step after the prediction engine. So once I know which are the service time, I can solve the problem, the routing problem. And this is where we have like a solver. What is a solver? The solver is basically, it's an algorithm that gives you, given all those inputs, gives you the solution of which truck is going to do which delivery and when. And in this case, what we do is that our approach is really to scout technology and understand which type of solver really works for us. In this case, we have two main performance dimensions that we always monitor, which are solution quality and solution runtime. Those are two very important metrics. Why? Because vehicle routing problems, they scale very badly. So the bigger the problem, much harder it is to solve it. And a very key thing here is that in mass industrial applications, solution time is nearly as important as solution quality. So the idea in this case is that in real life, sometimes it's very good to accept a certain optimality gap. So to accept a solution that is not optimal, but few points percentage worst, if we can get solution quickly. So given this consideration, in terms of technology and models, it means that we tend to privilege Metaheuristics and constraint programming over exact methods like mixed integer programming. So the idea really here is to give a great importance to the speed that is actually needed to get a solution. So the core of our solver is really based on local search. So we use Metaheuristics. We use actually many different Metaheuristics, which are based on, in reality, two big steps. The first step is the step of building solutions. And in this case, the idea is that we need, first of all, a quick and dirty initial solution, which can be, for example, just visit the point, the nearest point that is close to you, and then move on with the same logic. And then we also need to be able to build new solution fast. In this case, it means that we need operators, that's how they're called, which are able to give you a solution that, starting from the local one, from the current solution, they can give you the possibility to explore the neighboring solutions in a very fast way. And again, also in the evaluation of solution quality, the keyword is fast. So since the Metaheuristics is gonna try and look and explore for many different iterations, many different parts of the solution space, we need to evaluate solution quality in an incremental way. We cannot recompute the objective function from scratch every time. Then in moving around the neighborhood and in looking for better solutions, there are many things that have to be considered. First of all, we want to escape local minima. So by definition, the Metaheuristics don't really offer optimality. There's no guarantee for optimality, so we need to establish frameworks and rules that help us escape local minima. So, for example, we use framework like simulated annealing, where basically we accept a non-improving solution given certain logics. And of course, we also tend to treat constraints as soft constraints, which means that we allow solutions to be taken even if they violate the constraints, but then we get them with penalties so that we can explore the search space in a better way. This is an example of a very nice example that I'm going to play now of how a Metaheuristics for the traveling salesman problem works. The idea in this case is to the problem that I want to solve in this case is that I have the US map here. I have those points which represent cities, and I want to create a solution that is the solution to the traveling salesman problem. So basically, I want to visit all those cities in the most efficient way, so minimizing the total distance. What happens in this case is that the algorithm starts, and there is a first solution which is pretty bad, and then the algorithm kicks in. This is a simulated annealing with a certain temperature, which is moved during the implementation, and the solution starts becoming better and better. So in this case, the solution is already better than before. The more I give it time, then the better the solution becomes. And as we can see, we started from a total distance that was around 50,000 kilometers, and in reality, at the end, now it's starting again. In the end of the algorithm, the total distance is around 30,000 kilometers. So the idea is really to explore the search space at very fast incremental steps in order to get to a solution in a reasonable amount of time. Okay, we are very close to the end. In terms of what is going to come in the next month, We are really going to invest a lot in our product roadmap in the area of advanced analytics. First of all, we want to build a recommendation engine that is able to collect data directly, a recognition engine that is going to collect data directly from emails, PDF, and Word docs, because data integration for us is a pain right now because we have to integrate many different sources. So building automation there is really giving our client a lot of value. We also want to build a recommendation engine for load finding. And the idea here is that we want to be able to scout the opportunities that the spot market offer in an efficient way. And also for the routing part, right now, as I said, we are mainly using Metaheuristics and constraint programming, but there is a lot of interesting research going on also in hybrid approaches and also deep learning approaches for solving variable routing problems. And of course, there is something that we really want to explore. Of course, I'm not alone in this journey. So together with me, there are also Filippo, Erika, and Alessandro. And we are also very happy if you want to get in touch. As I said before, we are a seed stage startup based in Milan. So if you want to know more about us or just look for opportunities and have a quick chat, we are very open, and those are my point of contacts. So thanks a lot.